Okay, Calc, this is section 6.3. This is kind of a difficult section for me to teach to you through distance learning, but we'll try to make do as best we can. Not quite sure what the homework is going to look like here yet, but maybe else we'll go through. I'll kind of make a decision and figure out what we're going to do for this. So section 6.3 just kind of introduces you into basically the concept of 6.1 and 6.2 combined together and how they are related to each other. So antiderivatives is what we've kind of been working on. What an antiderivative does is it will find the area under a curve for a particular function, okay? So like this curve right here, what we would do normally in section 6.2 is we would write out all these rectangles and do all that stuff and add all those areas together and try to figure out what the area is. And even then, it's only an approximation, right? But what I can do is if I'm given the equation for this function, which looks like the square root of x, what I can do is I can designate where I'm going to start, so like at 0, and if I'm going to stop here at 1. My starting and stopping point is going to tell me where I'm going between, and then I can use my starting and stopping point and an antiderivative to figure out what this exact area is underneath of this curve, okay? And that's going to give me the exact area. It's not an approximation like the rectangle thing was. It will tell me exactly what the area is underneath of this curve up to the x-axis, right? This will not take into consideration the area that's below this, obviously, because there's like an infinite area below this. If I would shade this all the way down, we wouldn't have an area because it would just be an infinite area. So we're talking about like the area bounded by this curve and the x-axis here in between these 2 points, 0 and 1, okay? And so what that's going to look like is it's going to be called a definite integral, okay? If we were to set this up and find the antiderivative of the square root of x in the past, what it would look like is this integral symbol, and it would be the square root of x, and we would write dx afterward, okay? That's how we would know that we are trying to find the antiderivative, okay? This is an indefinite integral. Indefinite integral, okay? But if we want to make that into a definite integral, what we would do to change that is we would actually have the two numbers that we're trying to go between. So like 0 and 1 would be our boundaries, okay? They're called an upper limit and a lower limit, okay? Our lower limit would be 0 and our upper limit would be 1 because we're saying we want to find the area of the square root of x, the area that's under the square root of x, just from 0 to 1, just from this interval left and right here, that area going on there. And this makes this a definite integral because we are trying to find a definite area. He is now defined. Here he was not technically defined. We just had a general antiderivative for him. But this one, if we have 0 and 1, we're actually going to solve for and find a number as to what the area is. Okay, so this is a definite integral. Now, these guys are called your limits of integration. So if I talk about those, or if I refer to your limits of integration, those are just those two numbers that I'm bouncing between. Okay, so your left and right, or upper and lower limit. Okay, those are your limits of integration. All right, so let's kind of go down here and let's look and see what one of these examples is going to kind of look like. So this theorem 6.4 says if a function is continuous on a closed interval, then you can find the antiderivative, okay? So if there's no jumps, no holes, no funny business, I will be able to find the area of it underneath of a curve, which makes sense. If I have a curve of any sort, I can go ahead and find the area underneath of that curve as long as there's no holes or jumps or skips or anything like that, okay? So what they will do is they'll write our definite integral as some function dx, just like we had before, but now they'll have an a and a b. And so it will kind of look something like this, 2x dx. All right, and what this will look like is if I'm trying to think about what the graph of 2x dx from -2 to 1 looks like, I would, first of all, graph 2x, so like y equals 2x, okay? Y equals 2x is a linear function. I'm going to start at 0, and I'm going to go up 2 over 1. That's kind of what the function does, up 2 over 1, up 2 over 1, or down 2 to the left 1, so it's this line right here. And what I'm trying to do is I'm trying to find the area of that function between -2 and +1. Okay, so if I lump off -2 here, and I lump off +1 here, I'm basically trying to find the area in between those two that's like bounded by the x-axis and the line. Okay, so what's that going to look like? What that's going to look like is this area here, because it's bounded by the x-axis and bounded by my line. Here it's bounded by the x-axis, bounded by my line. So I have this area that I'm trying to find. Okay, that's what he will look like. All right, in this case, what will happen is this area right here is represented by a negative area, and this up here is represented by a positive area. Okay, now if I would combine both of those areas together, just think to yourself, would my area be mostly negative, or would my area be mostly positive? Okay, since my area in the negative is bigger than my area in the positive, right? It's -2 on this side and a +1 on this side. This area down here is going to be larger than this area up here. My overall area will be negative, which kind of is weird, a weird concept, because usually you don't have negative area, but you will for when we're dealing with functions, and negative area is just going to represent under the x-axis, okay? So that's kind of some differences and some things of how this works, okay? For section 6.3, they're not going to have us actually solve for the area yet. It's a very simple process, finding the antiderivative. It involves plugging some numbers in, like 1 and -2, but we're not going to get to that yet until we get to section 6.4. Right now, they're just going to have you kind of understand what this stuff means and you know, what it looks like. So this function, if I were to graph him and try to find the area of what he is, he would be this purple area right here. Okay, if I combine those two areas, it would be an overall negative. Okay, all right, so let's go to the back and let's talk about some rules here for finding definite integrals. So what they will say here, this first property goes with example 1, which basically says that if I am taking and I'm looking at a function and I'm going from like 2 to 2, okay, for this function, this square root of x squared plus 1, if I were to graph him, okay, I know square root looks something like this, whatever, blah, 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 right? I'm going from 2 to 2, okay, which means I'm starting at 2 and I'm ending at 2. And we're trying to find the area of that, okay? But from 2 to 2 gives me no width. Basically, it's like the two starting and ending points are the same point. So when you have your starting and ending point is the same point, your area is obviously going to be 0, because I'm not looking for any width in this little space right here on 2. He's just going to have 0 width or 0 area, okay? So anytime you have that going on, it doesn't matter what your function is. If your two numbers are going to be the same, you're like looking at the same piece on top of itself. So the area is obviously going to be 0. In this case, in example 2, this one's kind of written funny because normally we start with our lower limit here, and our upper limit is the upper number or the top number, okay? So I have a lower limit of 3 and an upper limit of 0. Okay, normally it would go from 0 to 3 rather than 3 to 0. So what we can do is the second property right here says that if you are going from B to A, okay, what you can do is you can flip those two numbers around and then make that area negative. Okay, so this would be the same thing as like saying the negative of the area from 0 to 3 of x plus 2 dx. Okay, so same thing, but the area is just negative now, and now I'm going from 0 to 3 like we would normally do. Okay, so that's just kind of what that second property says. Again, we're not going to be solving for anything yet. Okay, so I know this is really confusing because you don't yet know how to solve that, and you don't yet know what it means, but that's okay. We're gonna get there. Okay, all right. Last property, well, kind of the last property. Says that if I'm trying to to evaluate a function, what I can do is I can break that function into two separate pieces and solve them individually if it makes it easier to do. So some people might try to do this when they're finding the integral of, let's say I'm just going to use the example from the front side, 2x dx, and they're going from like -3 to +2, okay? What I can do is I can break that apart, and if it makes it easier on me, I can go from -3 to 0 of 2x dx, that area, and then I could add that to the area from 0 to 2 of 2x dx, okay? And if you think about what 2x dx looks like from the front side, anything that's on the left side of 0 is going to be a negative area. So this area is going to be negative. This area is going to be positive. So it might be more beneficial for me to look at the two areas separately than it would be to try to combine them all together, right? So separate those two out. And this property is just saying that that is totally legal, that I can do that, okay? Another time that you might want to do that is when you have an absolute value function, okay? So they're giving us an absolute value function here, and just the absolute value of x, like y equals absolute value of x. Think about what he looks like, okay? He will be a v that looks like this, okay? And what we're wanting to do is we're wanting to evaluate the area of that function from -1 to 1, okay? So -1 is about here, +1 is about here, if we lump that off, okay? And we're trying to find that area, so basically I'm trying to find this guy, and I'm trying to find this guy. Now, both of those areas are going to be positive areas, okay? So it's basically like those two added together, but to take the antiderivative of an absolute value function, we can't do that. So what we will do is, rather than going from -1 to 1, they will go from -1 to 0, and then they'll go from 0 to 1, and then add those two areas together, okay? So -1 to 0, 0 to 1. But instead of writing the absolute value, notice how they changed it. They made it -x on this side, from -1 to 0, because he is -x. He's going downhill, okay, from here to here. And now I'm really fuzzy. Sorry, they have focus. Okay, from 0 to 1, he is a positive x. Okay, that's what the absolute value function kind of looks like. Positive x from 0 to 1. So now I don't have to deal in absolute values anymore. Now I can just deal with, from 0 to 1, it's negative. From -1 to 0, it's negative. From 0 to 1, it's a positive x. Find those particular areas and add them together. Okay, and then they went ahead and said, they gave us a little hint here. We don't know how to evaluate these yet, but we will eventually. They've said that the area here is 1/2, the area here is another half, which is going to add up to be an area total of 1. Okay, and that's totally legal. That's a good use of the additive integral properties when you have an absolute value. You want to separate him out into two separate pieces. Okay. All right. So let's do this last little property down here, and then I have a couple of examples that I'm going to go through with you. So properties of definite integrals. This is kind of a fast video, I guess. So when we're evaluating antiderivatives, okay, they have the antiderivative of k, where k is some constant. This is just a number, times a function. And then I'm evaluating from a to b. What I can do, and a lot of times I will do, just to make my life easier, is I'll take that k and I'll bring him out in front of the whole thing, and then I'll just evaluate the integral by itself, and then just multiply that k through. So an example of that would be like this one. If I'm evaluating from -1 to 2 of 5x to the 4th power dx, okay? What I can do is, to make life easier, I don't want to have to deal with that 5 in the front, so I can bring that 5 onto the outside, just deal with the x to the 4th power dx, and then my final answer will just be multiplied by 5. So what this property is saying is that if I have a constant or a number inside of that thing, it's not going to change the value or change the way that I find the antiderivative. So I can just bring him out, have him chill out here for a little while, and then bring him back into my final answer by multiplying the whole thing by 5 at the end, okay? But then I don't have to worry about him when I take the antiderivative of x to the 4th power and that type of thing, okay? So you can bring that constant out in front. With number 2, with this property, it says that if I have 2 individual pieces that I'm evaluating, kind of like when we did this with indefinite integrals when we didn't have these numbers here, you can take that and split that into 2 pieces. So from -1 to 2 of 5x to the 4th dx plus, now I can do from -1 to 2 of 6x dx. I can basically take those 2 pieces, evaluate them individually, find the area of each individual piece, and then add them back together at the end. Okay, so I would find the area underneath of here, find the area underneath of here, and then I would add those back together, and that would be the same thing as trying to do them both at the same time. Okay, some people just find it easier to do it this way. So same thing, you know, no big deal there. All right. I put 2 examples down below here. These are actually examples from your homework, or from the book, I guess. And I'm going to look at this, and I'm going to kind of talk you through how we would set these up. So this example, they give us the function 25 minus x squared, and then they give you what the graph of 25 minus x squared looks like. Okay, x squared is a parabola. He's facing down because he's negative, and then the 25 is basically shifting him up to the point 25. Okay, so if it helps you to think about it this way, it's like negative x squared plus 25. That might be a better way to think of it. So parabola facing down up at 25, and we're trying to find the area underneath of that curve. Okay, so I've kind of sketched out the area underneath of there. Okay, what's going to happen is he's going to touch here at -5, and he's going to touch here at +5. And they are asking in the book for you to write out what the integral would look like. So they just want you to write it out basically in this form. Okay, like what he would go from, what to what of the function dx, what that integral would look like. Okay, so kind of think about this. I know my function will be 25 minus x squared dx. Okay, I mean, think about what 2 numbers would go, like where you're starting, where you're ending. Okay, so starting at -5, because that's where he touches the x-axis, ending at +5, and this is what my integral would look like. I will caution you, because make sure that when you have an expression inside of here, 25 minus x squared, you make sure you put these parentheses in, because if you don't, then it looks like 25, you're taking the integral of it, and x squared is attached to the dx, but they're like not attached together. Okay, you want to make sure that if there's an expression here that's more than one term, you will always put your parentheses in there, like this one does. Okay, so keep that in mind. This is what your integral will look like if this is your area. Okay. All right, and then the last one, this example, they want us to sketch basically what area you're trying to find here. So 3x plus 4 from 0 to 2. Okay, so I would start by graphing what the function looks like. Okay, so we're going to start with 3x plus 4. Okay, that means that's kind of like y equals 3x plus 4. It's a linear function. I'm going to start at 1, 2, 3, 4, and then I'm going to go up 3 over 1, up 3 over 1. Okay, and this is the graph of my line, and what I want to do is I want to find the area of that from 0 to 2 on the x-axis. So 0 is here, 2 on the x-axis is about there. Okay, and basically I'm sectioning him off, and I'm trying to find the area. Okay, now which area is going to be shaded? I'm wanting to find the area that's bounded by these 2 lines and my green line and the x-axis. So that's going to be this region right in here. So if I were to evaluate this integral right here, it would tell me how many units are underneath of this curve and exactly what that area is. Okay, so that's sketching the graph of what we're trying to solve for, the area underneath of that curve, like that. Okay. All right, so I'm trying to decide what I want you to do for homework even. If anything, I might just have you answer a bunch of questions in this video when I go through and edit it. Yeah, why don't we just do that? I might post some additional questions that are kind of like this at the end, so kind of be looking for those. But let's just go with, you don't have any additional homework besides watching this video and answering the questions. Just go through this video, and you won't have anything else to submit to me. So that, yay, that's kind of exciting. All right. Next video, we'll talk about 6-4 and actually solving for what this area is. Okay, not just showing you what it looks like, but showing you finding what this exact area is underneath of that curve. Okay, not by using the rectangle method because that was terrible, but a simpler way. All right, that's all I have.